Viewers like you make this program possible. Support your local PBS station.
A campfire on a beach ignites a window on the skies.
You cannot have an aircraft cockpit window break in flight because it's a very severe incident.
A priceless metal powers engines with maximum thrust.
Titanium is a great metal because it has high strength-to-weight ratio.
And the armor of samurai warriors inspires a seat at 30,000 feet. Together, they create a cutting-edge flying machine, the ultimate in air travel. Natural resources, critical moments in time, and human ingenuity forged the world's most awe-inspiring machines. From raw to ready. Every single day around the world, more than 4 million people fly on commercial jets. Those jets come in all sizes, but the fastest growing category is the essential regional jet. Carrying up to 100 passengers at a time, a regional jet takes off every 6.5 seconds in the US alone. They provide transport for over half of all American air travelers. To succeed, they need to be extraordinarily comfortable, durable, fuel efficient, and fast, like the Bombardier CRJ-1000.
We're doing all of this with jet-like, jet-capable speed. So you're not flying in a slow airplane that is at lower altitude, being bounced in the clouds or in bad weather. You're flying with the big boys over the clouds at 35,000 feet at the same speed as everybody else.
There are 4 surprising raw ingredients at the heart of this spirited jet. Silica. It's in the sand all around us. Made into clear, strong, tempered glass for the windshield. And super thin, resin-reinforced fiberglass, the shell protecting vital radar instruments. Titanium. From the Earth's core to the wings of a turbofan engine. Strong, light, durable. Lacquer, the tough second skin with an ancient history that makes high-traffic passenger seats super durable. And first, a raw material that makes this jet a remarkably efficient flyer. The body and wings must carry 42 tons to 30,000 feet over and over. It's a marvel of engineering, made possible by a long trip down a river and a clever aluminum alloy. (1886). Scientist Charles Martin Hall is obsessed with finding a way to extract massive quantities of aluminum from raw ore. It's a metal more precious and valuable than silver. Aluminum utensils even grace the table of Emperor Napoleon III. But the current chemical extraction method yields only small amounts. If Hall succeeds, he could be rich. After endless experiments, Hall finds an answer. He uses a battery to send an electric current through a solution of aluminum oxide and a mineral called cryolite.
This isn't one of those inventions that happened by accident. Hall needed to take cryolite and heat it to 1800 degrees Fahrenheit. But then he took it a step further. He added an electrical current that caused an electrolytic reduction, breaking the bonds between aluminum and oxygen. Oxygen floated to the top and aluminum to the bottom, leaving a pure metal.
Hall's patented process becomes a global success, and he begins mass-producing aluminum and aluminum products, like cookware, for a company that would become known as Alcoa, still one of the largest aluminum manufacturers in the world. 15 years later, in 1901, German engineer and metallurgist Alfred Wilm is working for a government defense laboratory in Berlin. He's tasked with finding a replacement for brass bullets, something lighter. He experiments with aluminum alloys.
Alloys are metals mixed with some other element. Those elements can change all sorts of things. They can change the melting temperature, conductivity, the atomic structure in the alloy. They can even change the strength.
One of the metals Wilm tries to alloy with aluminum is copper. He applies heat, bringing the metals to 932 degrees Fahrenheit, then cools them quickly in water. But his method is a failure. The alloy still lacks strength. Five years later, though, serendipity steps in. Wilm is still searching for a strong aluminum alloy. As before, he heats up his concoction of aluminum with a small percent of copper. Again, he gets the same result. Frustrated, Wilm decides to take off for a sail on the Havel River. He leaves his lab and his alloy behind. 2 days later, when he returns, Wilm makes a remarkable discovery. The alloy, having been left to rest for 48 hours, has hardened. It's twice as strong. This process, known as age hardening, becomes the key step in creating new, extremely strong alloys.
When the alloy is hot, but not red hot or molten, the atoms can move through the lattice. Copper atoms will move through the aluminum copper and attach with other copper atoms, forming nanometer-sized particles. These particles block deformation on the atomic scale. But it takes time for this to happen, which is why it's called age hardening.
Several years later, World War I is creating new demands for innovative engineering and alloys. The German military, hoping to gain an aerial advantage, deploys the first all-metal plane, called a Junkers, after the designer Hugo Junkers. But this steel behemoth has a problem. It's strong, but way too heavy. They find a solution: an aluminum-copper alloy. It's sturdier, lighter, and ready for battle. As proof, during one mission in 1917, a Junkers takes 480 hits. Still, the pilot successfully lands back at base, with the plane intact. An aluminum alloy changes warfare and the future of aviation forever.
The great thing about aluminum-copper alloy is its strength-to-weight ratio. It's light like pure aluminum, but it's much stronger. And that's really important at 30,000 feet when the pressure inside the plane is 3 times greater than outside.
Over the coming years, the aviation industry grows, and scientists improve aluminum-copper alloy by adding other metals. One new additive is zinc. It prevents the alloy from cracking. In World War II, B-29 bombers are the first planes made from this zinc-strengthened aluminum-copper alloy. And today, that super alloy is still the critical ingredient behind this regional jet's lightweight body.
70% aluminum because it's light, and we can shape it differently. When you want to build a green aircraft, like the CRJ, and using less fuel, well, aluminum and composite combined there make a very, very good product.
At a strip mill, making the tough outer skin of a commercial jet starts with giant aluminum alloy ingots that sometimes weigh up to 20 tons. Machines preheat the ingots and gradually press them thinner and thinner while maintaining their width. Once the aluminum is at the desired thickness, they cut it into sheets, the perfect material for the fuselage and wings of a regional jet. At the assembly plant, workers transform aluminum, copper, and zinc alloy panels into a 130-foot-long frame, capable of carrying almost 42 tons of plane and passengers, up to 41,000 feet into the sky. The jet's exterior is assembled in 4 steps. Skin fabrication, fuselage assembly, wing assembly, and first, surface inspection. A technician examines each alloy sheet for any imperfections. A removable blue plastic film protects the top of the alloy, so he lifts up the aluminum sheet to inspect the underside. The technician buffs any scratches he finds on the surface. Then he lowers the sheet to smooth the edges. This prevents the panels from breaking when stretched. Attention to every detail is critical. Next, skin fabrication. It begins with stretching. A worker oils the machine to protect the panels from friction. Then, the technician locks each piece into place. It takes up to 500 tons of longitudinal pressure to stretch and curl the copper-reinforced panels. Alfred Wilm would be amazed at how far his alloy has taken aviation.
When you build something out of aluminum copper alloy, you have to have great care. Unlike pure aluminum, which can be bent and deformed because it's ductile, aluminum copper is more brittle. If you bend it too far, it'll break.
Then, cutting. A technician lowers a template on top. To avoid scratching, he uses a soft felt-tip pen to mark his cuts.
Là, présentement, ce qu'on enlève tout ce qui est l'extra matériel. Présentement, la pièce est trop longue pour les bassins d'usinage chimique. Là, on la met à son plus petit possible.
Next up, body assembly, the fuselage. Underneath this copper-strengthened skin, an aluminum frame holds everything in place. To fabricate this frame, a giant machine called a CNC, a computer numerical control, cuts thick aluminum alloy pieces to precise measurements as water cleans off the metal shavings. With the fuselage's frame assembled, it's ready for its skin. Technicians carefully unwrap and inspect the finished panel. The protective blue film has been removed for installation, so they need to be careful as they align it to a completed portion of the frame and mount it. To secure it to the frame, the team prepares for riveting by cutting hundreds of computer-guided holes. They're perfectly spaced for maximum strength.
Distance between the rivets is critical. Too far apart and the pieces joined together can separate. But if the rivets are too close to each other, there's not enough material and cracks can form.
Okay.
Each rivet is hand set, using a rivet hammer gun and a bucking bar. The team makes it look easy, but it's a skill that takes years to master. One bad rivet could damage the skin's anti-corrosive layer, putting the structural integrity at risk.
One of the downsides of mixing copper with aluminum is it makes it less resistant to corrosion. Often, they'll anodize the surface to protect it, a process that thickens the oxide layer. The problem is, if this gets scratched, it leaves the alloy exposed to the environment.
Next, workers put in 5,000 hours to build the final structural piece, the wings. A large crane guides the frames into a vertical position. Workers align aluminum alloy panels to cover the wing's 833 square foot surface. Last, cranes move the 6,750-pound, 86-foot wingspan to another station and stabilize it horizontally. Over 3 days, technicians worked tirelessly to install flaps, the movable pieces of the wings that increase lift on takeoff and reduce speed on landing. The massive fuselage and wings are now ready to become an amazing aircraft body with a light and super hard skin, able to hold up under incredible pressure. All thanks to innovators like Alfred Wilm and an aluminum copper alloy. Hardened aluminum makes a solid body, but the windshield must be just as strong. Flying at 30,000 feet and more than 500 miles per hour, the impact of a stone or bird can be catastrophic. To protect the plane, the crew, and the passengers, jets need super strong windshields made of glass, a versatile transparent material discovered thousands of years ago at a feast by the sea. And its secret ingredient is silica. 5000 BC, a Phoenician cargo ship near the Syrian coast is transporting a natural sodium carbonate used for cleaning called natron. The sailors have come ashore for the evening and are preparing a meal. They realize they have no stones on which to rest their pots, so instead they use blocks of natron. That night, when the sailors put out their fire, they make a strange discovery. Where there once was natron and silica-rich sand, there's now a hard, brittle, transparent substance.
Mediterranean sands are rich in silica. Normally it takes 3,000 degrees to melt silica, but when you add natron, it reduces the melting temperature to the point where a cooking fire can melt the material. Once it cools, you're left with a silica glass.
Today, glass is made almost the same way, but on a massive industrial level. Raw silica sand is mixed with sodium and limestone and heated to over 2,500 degrees Fahrenheit. For stronger glass, lithium is added to the mix. Soon, it turns into a thick, clear liquid. That molten liquid is poured into a large bath filled with molten tin. The dense tin rests at the bottom, while the lighter silica floats to the top, creating a perfectly flat sheet of glass. But truly strong glass requires one more step: chemical tempering.
To temper the glass, you put it in molten sodium nitrate. This doesn't melt the glass, but it heats it up and it expands the lattice. Lithium ions are able to move or diffuse out of the glass, and they're replaced by sodium atoms. Once this is cooled, the lattice compresses back down, leaving a harder glass.
For this commercial jet, the tempered glass windshield made from silica is installed in 3 steps: frame build, glass prep, and mounting. First up, building the windshield frame. A cockpit window must be completely fail-safe. Thanks to a multi-layer design, this chemically tempered glass windshield is as strong as it gets.
The cockpit windows, they're multiple ply because you want them to be extremely resistant to contain aircraft pressurization, but they also have to be resistant to external objects, birds and other things that could hit the windshield.
But a chemically hardened, multi-ply windshield is only as strong as the frame holding it in place. To build a solid windshield frame in the machine shop, technicians attach aluminum alloy bars onto mounting planks. The planks enter a fully enclosed, computer-controlled CNC cutting machine. Inside, the machine turns a raw hunk of aluminum into an intricate, finished frame section. Then, holes are drilled for the mounting bolts. The technician uses a metal template to guide the drill placement and angle. This is critical work. Jet windshields have tremendous cabin pressure pushing outward. One slight error in putting in the 314 bolts could cause the glass to fit incorrectly in its frame. Next, cleaning and prep. Over 3.5 hours, technicians meticulously unpack and clean the 100-pound tempered glass windows. They leave the protective coating on the glass to guard against scratches while cleaning. It's critical to remove any debris from the rubber gaskets around the rim. Anything left on the gaskets could keep the windshield from sealing properly.
Well, my job is important for touching this piece because I have to make sure there is no scratches. I gotta do a visual check. If ever there is a scratch, we raise a flag.
In addition to careful cleaning, he installs strips of insulation over the bolts. It's an extra necessary measure to ensure an airtight seal.
We have certain ones that go on the left and certain ones that go on the right. This seems to be the good one. Once I'm ready and I figured out I have the right one, I take out the sticker, try to follow as much as possible the holes with the bolts.
Now, installation. Two technicians carefully set the glass into the window frames and lock them in place. Each bolt is numbered, so the glass is set evenly onto the frame and leak-proof. A quick dab of sealant, and they hand torque over 300 bolts.
The cockpit is pressurized, so this has to be very well screwed on with the proper amount of sealing on the joining of the two windshields. During the 5-hour installation, flushness of the screws are very important, and we have to follow a sequence in installing the screws.
The installation is complete. The cockpit window is ready to give the pilots a clear, safe view of the skies, thanks to an ancient feast on a beach and silica. The windshield provides a clear view of the runway. To lift off, it's time for serious power. Getting over 90,000 pounds to cruising altitude takes enormous engines, capable of delivering over 14,000 pounds of thrust. At the front of these engines are remarkable durable fan blades that are light, strong, and resistant to extreme heat. Their critical ingredient was accidentally discovered by a humble English pastor out for a stroll: titanium. (1791), England. Clergyman and amateur geologist William Gregor is exploring Cornwall's Menishin Valley when he spies an unusual black sand on the banks of the Helford River. Back at his home, he examines it closely. It's a magnetic substance resembling gunpowder. Gregor believes it's made of iron, oxygen, and one other mysterious ingredient that he can't identify. He reports his finding to the Royal Geological Society. Unaware, he's discovered what will become one of the most valuable elements in the world. 4 years later, while exploring in a small Hungarian village, German chemist Martin Klaproth finds that same unknown element in a different reddish mineral called rutile. He isolates it, compares it to Gregor's sample, and confirms that they're the same. He names the element titanium, after the powerful opponents of the Greek god Zeus, the Titans. 115 years later, in 1910, scientists are still searching for a way to isolate pure titanium. They're convinced it's a useful metal, but it's incredibly difficult to separate from other elements. Chemistry professor Matthew Hunter has a remarkably simple idea. He believes heating just titanium tetrachloride and sodium in a sealed container, free from air, will make pure titanium and table salt.
Sodium and chlorine love to be together. They form salt. What Hunter needed to do was take his compound of titanium and chlorine and put it in a closed environment with sodium. and then raise the temperature to weaken the bonds. The sodium and the chlorine bound together, making salt and leaving titanium metal.
But creating a chemical reaction in a sealed environment can be explosive, as energy causes the elements to expand. For safety, Hunter takes over the college football field and crosses his fingers. His experiment is a success, but it only generates a small amount of incredibly light, hard titanium. For real-world use, engineers need more of the metal. The solution arrives with World War II and metallurgist William Kroll. Fleeing the Netherlands, he lands in the United States, bringing with him a revolutionary method to extract titanium in large quantities, using magnesium and heat. His groundbreaking work gets the government's attention.
Titanium is a great metal because it has not only a high strength-to-weight ratio, but also a high melting temperature. Aluminum has a high strength-to-weight ratio, but a much lower melting temperature. The only other metal comparable to titanium is beryllium, and we don't use it because it's toxic.
Two decades later, with Kroll's method and a plentiful supply of this precious metal, the United States Air Force designs a new fleet of 32 revolutionary reconnaissance planes. Built for extreme speeds and altitudes, Lockheed's SR-71, or the Blackbird, is 93% titanium alloy. It climbs to 85,000 feet and moves at 2,200 miles per hour. It still holds the record for the fastest manned jet ever, thanks to titanium. Today, the Kroll process is still used for titanium production. First, titanium-rich rutile ore is pulled from the earth. It's heated and mixed with chlorine gas, then molten magnesium and brought to 1,600 degrees Fahrenheit for 4 days. The result is a porous hunk of pure titanium called a sponge. Next, sponges are crushed down into pebble-sized bits. Then, using 7,000 pounds of pressure, they're compacted into blocks called ingots. At factories around the world, these ingots are heated to 2,134 degrees to make the titanium malleable and molded into vital parts and products. The aviation industry uses 2/3 of all this titanium. At GE Aviation in Durham, North Carolina, titanium fan blades are installed in this high-flying regional jet's CF-34-8 turbofan engines. It takes technicians close to a week to build each engine by hand, using almost 8,500 individual parts. One of the key components of this turbofan is its huge titanium front fan. It draws air through the compressor into the combustion chamber, producing thrust. But it also pushes air through the bypass duct surrounding the engine core, creating additional thrust. In fact, close to 80% of the total thrust is produced by this bypass air.
This is an engine that develops 15,000 pounds of thrust and weighs about 2,000 pounds. So very efficient engine that also is efficient in terms of fuel usage.
There are 3 critical steps in building these turbofan engines: rotor balancing, building the engine core, and the titanium fan blade installation. First, rotor balancing. To maximize the combustion of fuel, a series of 10 tightly spaced discs, called a rotor, pressurizes air coming into the engine. Any imbalance of these rotating blades can send powerful vibrations through the plane. To begin, a technician lifts the rotor into a balancing machine. Simulating actual use, it spins at 1,300 revolutions a minute.
Vibrations are the enemy of any engine. And it's especially true in a jet engine working at high RPMs. Any imbalance can cause bearings to fail or tight tolerances to be lost. And when this happens, boom, the engine can explode.
To balance the rotation of these discs, the technician carefully removes individual rotor blades. He installs tiny weights to shift the balance. Then he runs the machine again to see if the weight corrects the problem.
And so now we can see that the rotor is balanced. Now we can finish up and then send it on down the line so that it can go into the engine.
Next, it's time to build the engine core, the part of the engine that ignites fuel and air to keep the titanium front fan spinning at full speed. The engine core build process takes 290 precision steps. Here, technicians begin to assemble the core from the ground up.
Pretty much requires two people. It's best if you have one guy work one side, one guy work the other, because you're mating all of these assemblies. You have a big split flange here, and you do it, in parallel. Keeps it all even.
Finally, it's time to build the most critical turbofan component, the titanium front fan. To generate enormous thrust and feed the engine core with air, these blades are big. That's why titanium, with its incredible lightweight, is so important.
The advantage of these metals that are different than your typical steels are their strength-to-weight ratio. Weight is a huge issue on these airplanes. The lighter we can make the airplanes, the more efficient the airplanes are.
Designed for a snug fit, technicians install the 28 titanium fan blades to the rotor, using corresponding pins and bushings. They're carefully counterbalanced, creating an even fan rotation and a smooth flight.
There's 28 blades on this particular model. They're dynamically balanced as a set, the 28. So the weight of each of them counterbalanced, so as this is rotating, it just creates a smooth, no vibration, because this is the thing, if it vibrates, potentially it causes a rumble to the cabin. So it's critical that this runs smoothly.
After 80 hours of balancing, assembly, and inspection, 2 CF34-8 turbofan engines are complete. Once they're fired up, they'll propel the CRJ-1000 faster than any other regional jet. An incredible feat, made possible by an amateur discovery and titanium. The engines are ready for takeoff. To set a course requires a high-tech sensor. Guiding the regional jet around the globe is a sophisticated and sensitive radar system. It's a vital instrument for tracking dangerous storms and nearby air traffic. To shelter this critical equipment from Mother Nature, while still allowing vital radio waves to pass through, jets are fitted with a protective shell called a radome. Its key raw ingredient is the same silica used in the windshield, but this glass takes on a different form, inspired by a simple, primitive combination of sticks and earth: fiberglass. (8,000 BC). Humans need a sturdy construction material made out of basic ingredients. They find a solution in a combination of wood and clay that we now call wattle and daub. It's one of the first composites, a combination of 2 ingredients that make a super strong material.
A composite is when you take materials with dissimilar physical properties and put them together. In the case of wattle and daub, sticks are the structural support. The clay, on the other hand, not only insulates, but protects the wood.
Over 9,000 years later, and Mongolian horsemen are sweeping into Europe, devastating opponents as they build an empire. The secret to their success? The composite bow. Using animal glue to fuse together layers of wood and bone, the Mongol bows are compact powerhouses of destruction. This technological innovation in warfare is the foundation of their empire and helps them conquer much of the world. civilizations continue to innovate with composites. And in 1932, chemist Dale Kleist is working at Owens, Illinois Glass, a company searching for new advanced uses for this everyday silica-based material.
Kleist is trying to fuse two glass blocks together by spraying molten glass in between them. But what happens is, as he's doing this, it doesn't pour in between the glass blocks. Instead, it comes out as tiny fibers.
His colleague, John Thomas, is thrilled. He sees this as a potential breakthrough glass product for the company. He and Kleist immediately get to work, replicating the accidental discovery. 6 years later, Games Slater, an engineer and colleague of Kleist and Thomas, takes the innovation one step further, designing a way to make these glass fibers in massive amounts. He creates a stream of 2,100-degree molten glass. As it exits, it's hit with a blast of steam, creating long silica glass filaments. These strands fall onto a conveyor and gather together to create what Slater calls glass wool. The first invention with this new material is home insulation. The modern composite we call fiberglass is built on Kleist, Thomas, and Slater's inventions. Silica glass fiber is mixed with epoxy. The materials work together to create a super strong composite.
Glass is strong and hard, but it's brittle. Epoxy isn't strong, but it's very tough. You can bend it over and over before it breaks. Combining the two, you get the best of both worlds, a light material that's fracture resistant.
Today, we use fiberglass for everything from housing insulation, to boats, to aviation. One of the key aviation fiberglass products is a moldable material called thermoset sheets.
The term thermoset literally means temperature hardened. When you cure these sheets in an oven, the long molecules attach to one another until the material's fully hardened. But this happens even at room temperature, and to store them for a long time, they need to be frozen.
At Bombardier's Saint-Laurent facility, silica-strengthened fiberglass sheets are stored in a freezer at 0 degrees Fahrenheit until it's time to build the radome in 3 essential steps: fiberglass layering, radome assembly, and flight deck installation.
The main benefit of using fiberglass is allowed radar radio wave to go through to the tower control on the ground so that you can track the aircraft while it's in the air.
First up, fiberglass layering. When the technicians are ready to build the radome, they pull the frozen fiberglass sheets from storage and bring them into this climate-controlled room for preparation. The air in this room constantly circulates to prevent dust particles from contaminating the fiberglass.
On le prépare et dégèle. Après ça, on le rentre en dedans. On le met en position pour que la machine puisse le prendre.
To create the multiple layers needed for perfect radome thickness, a laser cuts several sheets of fiberglass at one time with extreme precision. Next, a craftsman carefully positions layer upon layer of these fiberglass sheets to fit perfectly inside a cone mold. To form the tip of the cone, he uses a heat gun to apply just enough heat to stretch and shape the fiberglass sheet without fully curing it.
Each layer of fiberglass is about 1/10,000 of an inch. The worst part of this one is to stretch it and not stretch it too much so you'll have problem installing it afterwards.
It takes 5 hours to completely layer a single radome by hand. Then, the radome heads to a 250-degree Fahrenheit pressurized oven called an autoclave, where it sits for 1 hour until it hardens. It's a strong, solid shell. Dale Kleist could never have imagined when he accidentally discovered fiberglass. Next up, radome assembly. The cured fiberglass shell moves to the fabrication station, where workers cut it to the specified size and mount a ring that will seal it to the plane. They securely attach it, ensuring it can endure extreme air pressure at high speeds.
We're going to install a lot of brackets. We're going to fix the ring with some rivet. This is the latch. It's like the doorknob of the plane. This is the spigot. This is the critical part. They have to be at its place to connect perfectly with the plane.
But coming loose isn't the only danger a radome faces mid-flight. On average, lightning strikes every commercial plane at least once a year. And because planes naturally have strong electrical fields at their extremities, lightning loves to make contact with the radome.
The whole point of making the nose from fiberglass is that it doesn't conduct electricity. But this is a major disadvantage when lightning strikes. The average bolt is 30,000 amps, and when it hits, it's more than enough to fry both the radome and the radar underneath.
To protect the radome from these mid-air strikes, technicians attach metal rods. They'll absorb lightning strikes and disperse the energy through the body of the plane, protecting the radar system. Finally, in flight deck installation, the technicians align and bolt the fiberglass radome to its hinges. They also inspect latches along the edge to make sure the radome closes properly, keeping its vital instruments safe while maintaining the aerodynamic shape of the nose. The radome is now complete. It's ready to protect the radar system from high-voltage lightning strikes without blocking critical signals, all thanks to ancient building techniques of sticks and mud and silica-strengthened fiberglass. The brain of the jet's fully protected. Now, let's put the passenger in passenger plane. Over its lifetime, a single regional jet carries up to 3.75 million passengers in safety and comfort. Each of the 100 heavy-duty leather seats inside a commercial aircraft must endure years of wear and tear. And the secret to their longevity is as old as samurai warriors. Lacquer. 1185 AD, Japan. Ancient warriors are battling with an enemy clan. Arrows are flying, swords are swinging, and these horseback warriors are shielded by armor made mostly of leather. It's initially effective, but exposed too long to Japan's wet, humid climate, and the porous animal skins soften and break down.
The main ingredient in leather that makes it durable is the protein collagen. It's a long molecule held together by chemical bonds and physical tangling. It's a strong network, but there's space in between where water can get in and cause deterioration.
The artisans who make the samurai's armor discover the unique qualities of urushi, a milky sap from native trees. Spread over the leather and left to dry in moist air, it hardens into a durable second skin.
Thick layers of sap from the urushi tree fill in spaces between the collagen, keeping out the water. Plus, there's an added benefit for samurai warriors. It makes the leather very hard, a perfect defense against an enemy's attack. But one major downside of using urushi sap as a lacquer is its main active ingredient, urushiol, which is the same toxic compound found in poison oak and poison ivy. In other words, you don't want to get it on your skin.
But warriors are willing to suffer. The sap forms a stiff protective coat, making the leather impenetrable to the elements and piercing enemy weapons. Still, it's not perfect. Over time, this natural lacquer breaks down. In the 1950s, scientists experiment with natural lacquer alternatives, synthetic resins. Made from byproducts of petroleum refining, like acrylic acid, they work faster and last longer.
A synthetic polymer like acrylic can provide similar protection against water, but it has the added bonus of longer molecules, which makes it more flexible.
When applied, these acrylic lacquer sealants quickly bond with the protein layer of the treated hide. They produce a shiny protective coating that's resistant to spills and holds up to the constant friction. They're perfect for a jet passenger seat. At BE Aerospace in Winston-Salem, North Carolina, acrylic sealed leather is used to upholster a passenger seat in 3 steps: frame construction, upholstering, and finishing. First up, frame construction. Here, workers bolt together strong, lightweight aluminum alloy bars to provide support for the jet's double seating arrangement. To increase efficiency while ensuring solid construction able to withstand 16 Gs of force, workers use multiple tools set to just the right torque specification. Next, assembling the frame's 3 armrests. First, they route a cable through the aluminum sheet metal base that controls the recline function of the seat. The armrests are then capped with injection molded polycarbonate plastic. Last, they connect the assembled pieces, and the frame is complete. Next up, upholstering. Regional aircraft seats must endure the weight of millions of passengers. But durability isn't the only concern. To match the longevity and comfort of lacquered leather upholstery, BE uses a patented woven polyester material called Crystal Flex to make their seat diaphragms. It's as tough as aluminum, but with way more flexibility. A perfect cradle to support the bottom seat cushion for thousands of flights. It's the kind of toughness that ancient samurai warriors would appreciate.
Bring it up to the front, pull it over, walk it on there, stretch it, release it into the position it is on the front, and then make sure that the seat's smooth, there's no wrinkles in it.
Then, a technician pulls a non-flammable foam padding over an aluminum sheet metal back panel, and the seat is finally ready for its cover. While the thick lacquered leather is easier to clean than fabric, it's more challenging to install.
Synthetic polymers are more flexible than hard lacquers like urushi sap, but the bonds between the polymer chains still affect the leather's ability to stretch. The chains want to snap back into position. This makes it a bit tougher when you're trying to get a tight fit over a seat cushion.
Finally, a technician mounts the seat backs onto the frame. And the finishing touch: treated leather upholstery on the bottom foam cushions. A final inspection of the seats, and the jet is ready for boarding, thanks to the ingenuity of Japanese warriors and lacquer. "18 months of skilled labor have turned 4 powerful raw materials into the essential parts for a sleek, efficient, ultra-safe jet. Now, it all comes together for final assembly. 85 technicians work around the clock to finish the 51,000-pound plane. The final assembly happens in 4 steps: painting, interior cabin, engine housing, and first up, body and wing assembly. At the loading dock, workers greet the flight deck, attach it to an overhead crane system, and move it to the main hangar. Here, they carefully connect the flight deck with its fiberglass radome and tempered glass windshield to the aluminum alloy fuselage. Next, the rear section is connected onto the back of the fuselage, and the body is sealed. On the other side of the hangar, an overhead conveyor lowers the wingspan onto jack stands. Now, it's time to marry the body to its wings. 2 massive cranes lift the long 130-foot fuselage and lower it onto the 86-foot long wingspan. workers align joints in the center fuselage with the wings. It takes them 12 hours to securely fasten these two major parts of the aircraft. Next, in painting, the assembled jet is ready for its colors. Craftsmen spend 3 days painting all the fine details onto the jet. Meanwhile, workers install interior cabin components by hand. They bolt the lacquered leather seats into tracks along the floor and walls. Last, workers install the twin engines and connect them to the fuel line. Finally, the CRJ-1000 is complete and ready to take to the skies. Giant titanium fan blades generate lightweight, powerful thrust at takeoff, while tempered glass made from silica gives a safe, unobstructed view of the sky ahead. Ascending to 30,000 feet, the hard aluminum-copper alloy fuselage withstands intense cabin pressurization. And the silica-strengthened fiberglass radome allows radar signals to pass, so the pilots can steer clear of foul weather. And all throughout the flight, super durable lacquer-covered leather seats provide comfort to keep passengers at ease.
Way before Da Vinci's flying machine or the Wright brothers' first launch, humans have dreamed of flying. But soaring at 30,000 feet takes a lot more than a dream. It takes the most amazing natural resources on the planet and thousands of years of technology to push those raw materials to their very limit.
From natural elements to one of the world's fastest and lightest jets, the Bombardier CRJ-1000, built from raw to ready.